Welcome to the new session that is about subgroup and classes. I am your instructor Saurav and we'll be talking about subgroup and classes in a couple of minutes ahead. So let's begin our work. We'll quickly go through the properties of a group. As we have discussed earlier, a group is a collection of 4 points that is applied to a set, and if it happens to fulfill all the conditions imposed by a set, then it is termed as a group. The 4 postulates are: number 1, the product of any 2 elements or the square of the element must be an element of the group. Number 2, one element of the group must commute with all other elements and leave them unchanged. It means that element of identity must exist. Third point is the associative law of multiplication must hold. It means that the 3 members must associate. And the fourth point, the reciprocal element for every element must exist within the group. So these are the 4 set of conditions that are there for a group. We'll move now to another important topic, that is subgroups. Smaller groups that may be found within the larger groups are called as subgroups. There are of course groups that have no subgroups other than the trivial one of E itself. And there's a property: the order of any subgroup G of a group of order H must be a divisor of H. So it concludes that H upon G is equal to K, where K must be an integer. So this expression restricts the number of possible subgroups within a group. We are more interested in classes. There is another way in which the elements of a group may be separated into smaller sets, and such sets are called classes. Before going any further, let us understand a technique of similarity transformation. If you have something like this, so an element, if you choose A and another element you choose an X, so that X inverse AX is equal to B, then we say that B is a similarity transform of A. So what are the properties? Every element is conjugate with itself. This is the first property that we have discussed, that A is equal to X inverse AX. Obviously A, X and A all must belong to the same set. The second property, if A is conjugate with B, then B is conjugate with A. For example, if you have a certain element X such that X inverse B into X is equal to A, then there must exist some element Y such that Y inverse A Y is equal to B. So B transforms as A and A transforms as a B with different elements. Both the elements must belong to the same set. The third condition and the third postulation about this is, if A is conjugate with B and C, B and C are conjugate with each other. So this is the third point. It is better to understand by certain examples. We'll begin with the example of water molecule, that is C2V point group and C3V point group. So we have defined that a class is a complete set of elements that are conjugate to one another, and significance of the class lies in the fact that in construction of character table or specific point group, we first need to identify classes within that point group, because further we are going to apply the great orthogonality theorem, which would be talking about the classes. So the first work would have been to identify the classes of a particular point group. So if we start with water molecule belonging to C2V point group, this is the group multiplication table that we have learned earlier is for C2V, and now we are going to see how different elements are transformed. We are going to examine them one by one. So start with identity. Now when you start with identity, E inverse. So E inverse is E. Reciprocal of E is E itself. The answer is E. But when you talk about C2 with E, so C2 inverse E C2, reciprocal of C2 is C2 itself, and C2 into E would be C2. There are two C2s, and C2 is reciprocal to itself. So C2 multiplied by C2 is identity. So the second result is also identity. Now the third element would be sigma V. So when we do sigma V inverse, E sigma V1 should be equal to, reciprocal of sigma V is sigma V itself. We know all planes are reciprocal to themselves. So sigma V and this product is of course sigma V. So the two sigma V's make identity, and the same would be the case for the fourth element also, sigma V dash, E sigma V dash, which results ultimately in identity. So what we see is that each element ultimately gives the result of identity, and hence E is a separate class of its own. Shall we examine for now C2 symmetry element? For C2 element, we'll start with identity. So E inverse C2 into E, first element is this. So the product is C2. If we talk about the next element, C2 inverse, C2 into C21. So C2 inverse, the reciprocal of C2 is C2 itself. This is C2. This is another C2. The three C2 make one C2 because two C2s would be identity. So one C2 would be the result. Now, if you proceed for sigma V, so sigma V inverse C2 sigma V. Now, reciprocal of sigma V is sigma V itself and product of sigma V into C2. Now, sigma V and C2, they are giving you the product is sigma V dash. So, this is a sigma V dash into sigma V dash into sigma V is resulting into C2. So the fourth element is also C2. So let us continue with the sigma V dash. We'll find that the answer is again C2. So conclusion that we are going to make is C2 is a separate class of its own. That's very fine indeed. Now, the remaining two elements, sigma V and sigma V dash. So just go for sigma V. If we start with identity, E inverse sigma V E is equal to, of course, sigma V. C2 inverse sigma V into C2. Now, C2 inverse, that means reciprocal of C2 is C2 itself, and C2 into sigma V. C2 into sigma V, you will find that sigma V dash, and sigma V dash into C2. So, sigma V dash into C2 results in sigma V. So, answer is sigma V. Similarly, go for sigma V inverse sigma V. Elements reciprocal of sigma V would be sigma V. There are three sigma V's in a row. Two sigma V's make identity. What is left is sigma V. Answer is sigma V. Now, the last one is sigma V dash, sigma V dash. So, sigma V dash is actually reciprocal of sigma V dash is sigma V dash itself, and sigma V dash into sigma V dash into sigma V, that results in C2. So, this is C2 and C2 into sigma V dash. So, C2 into sigma V dash is going to yield you sigma V. So, the result is sigma V. So what we find that sigma V is a separate class of its own. About sigma V dash, if we proceed in the same manner, you will find that the element sigma V dash transforms by identity to sigma V dash. Sigma V dash transforms to sigma V dash by C2. It also transforms by sigma V to sigma V dash itself. And the fourth element, sigma V dash, transforms sigma V dash to sigma V dash. And thus, we conclude that the similarity transformation of sigma V is also a separate class of its own. So what we have seen ultimately, that each element identity C2, sigma V dash, they form a separate class, and this fact would be very useful in construction of character table when you are going to exploit rules of the great orthogonality theorem. Let us take another example. Say start with ammonia molecule belonging to point group C3b. So when you talk about C3b point group, you know that it has 6 elements: identity, C31, C32, sigma B1, sigma B2, and sigma B3. And here is the group multiplication table for C3 point group. Now we have to examine how does E transforms by all the rest of the 6 elements. Now it's quite easy to understand that E is E. C31 inverse E C31. Now C31 inverse means C32. Actually, reciprocal of C31 is C32. So C32 into C31 makes it C33. That is identity. So the second is identity. When you talk about the third element, C32 inverse, the reciprocal of C32 inverse is C32, it's C31. So it is C31, and C32 into identity would be C32. So 2 and 1 makes C33, that becomes identity. In similar manner, when you talk about the planes, sigma B1 inverse, you will get identity because reciprocal of the plane is the plane itself. So sigma 1 inverse is equal to sigma V1 itself. So sigma V1, that gives identity. And in the same manner, we'll proceed for the second plane and also for the third plane. In all cases, the result is identity. So the conclusion that is before us is E is similarity transformed to itself, and the element E therefore belongs to the class of the group. Now we have to see how does C31 and C32 transforms in this manner. So similarity transformation of C31. So let's begin again with identity. So identity C31, that's equal to C31. That's okay. Now C31 inverse C31 into C31. Now you just say C31 inverse is C32, and C31 into C31 is C32. That makes it C34, and C34 is equal to C31 because means C33 into C31. So C33 is identity, of course. What is left is C31. Similarly, if we proceed for C32 inverse, now C32 inverse means is the C31 itself. So C31 and the C32 into C31, that is C33, and C33 is identity. So the result is finally the C31 itself. And let's see about planes. So sigma V1 inverse C31 sigma V1. So the result is reciprocal of sigma V1 would be sigma V1. Sigma V1 into C31. Now sigma V1 here and C31. their product is sigma V2. So here is sigma V2. So we get sigma V2 here. Now sigma V2 into sigma V1. So sigma V2 into sigma V1, the result is C32. So what we find here is C32. Now if we talk about sigma V2, so in case of sigma V2 reciprocal of sigma V2 would be sigma V2 itself, and sigma V2 into C31. So sigma V2 into C31 is going to yield sigma V3, and sigma V3 into sigma V2. So sigma V3 into sigma V2, that gives you the product of C32. So again the result is same. Likewise for the third element also the result would be the same, C32. So what have we observed? The similarity transformation of C31 always gives C31 and C32. Thus, the operation C31 and C32 belongs to one class of the group of C3V. You can just examine for C32. When you do it, you just look out it. E inverse C32E is equal to E into C32 is C32. So there is no question into it. But when you talk about C31, C32, C31, so C31 inverse, C32, C31. So inverse of C31 would be C32, and C31 into C32 is C33. This is C32 and this is C31. So this is C33. This is ultimately, this is C32. C31 inverse is equal to C32, and C31 and C32 gives identity. So the result is C32. There is some mistake here. Anyway, you can understand it. So when you talk about third element, C32 inverse, C32. So C32 reciprocal gives C31. This is C34. C34 and C31, that is C35, that is equivalent to C32 because C33 is identity. Go on with the different communication, different manipulations in this way. You find that with the planes, the result for C32 comes out to be C31 only. So conclusively, we say that the similarity transformation of C32 always gives C31 and C32. Thus, the operations C31 and C32 belong to one class of the group. Similarity transformation of sigma 1 can be done in the same manner. Start with identity. E inverse sigma VE, result is sigma V1. Similarly, C31 inverse sigma V C31, that is result is sigma V2. Similarly, C32 inverse sigma V C32, result is sigma V3. Now take sigma V1 inverse sigma V1, result is the reciprocal of sigma V1 is sigma V1, and the two sigma V1 would be of course identity. So the result is sigma V1. If you proceed like that, sigma V2 reciprocal is sigma V2, and sigma V2 into sigma V1. So just look, sigma V2 into sigma V1, that produces C32. So it is C32. Now if you want to find out C32 and sigma V2, so C32 and sigma V2, this is going to give you sigma V3. And likewise, we will finally find that similarity transformation of sigma V1 by sigma V3 gives sigma V2. So the similarity transformation of sigma V1 always gives sigma V1 or sigma V2 or sigma V3. Thus, these operations must belong to one class of the group of the point group of C3V. You are advised to obtain similarity transformation for C2V, sigma V2 and sigma V3. Check yourself and you can be assured that they form the three elements. They have the same point group, sigma V1, sigma V2 and sigma V3. They belong to the same class. This you can check it yourself. If you want to notice what are the significance, just look at this. We have proved that E belongs to one class, so E is written separately in the character table. C2 belongs to C31 and C32 belongs to one class. So the two C3 are in one class written collectively. Similarly, three vertical planes have been shown here belonging to one class. If we talk about D3H point group for flat molecule like boron trifluoride, E is a class. C3 has two elements belonging to same class. C2s of three types are in the same class. Sigma H is making a unique class. S3 is in the class 2S3 and 3 sigma Bs are also in the same class. Similarly, you can go for the rest of elements. So now you can understand the importance of classes within the group that helps us to find the great orthogonality theorem and character table construction. Thank you for watching. Thanks again.